Hello everyone, and this is question 7 of mock set 5 paper 1, and we have a question here on the trapezium rule. Normally these questions are quite nice, just got to be careful of one or two little twists and turns. I think one of the most difficult things about this particular question, this type of question in recent years on exam papers, was that recently there was one where they didn't even tell you to use the trapezium rule. And that particular question, I believe it was about a plane taking off a runway or something, and they basically gave you the distance of the plane or the speeds of the plane at various points on the runway, and what they expected you to understand is that the area underneath the velocity time graph gives you the distance covered, and that was the reason why you needed to use the trapezium rule. So that was a little bit tricky a couple of years ago when there was a question where they didn't say to use the trapezium rule. Kind of caught quite a few people out. However, for this one, they're being nice, and it does indeed tell us that we should use the trapezium rule, so that's nice. Let's have a look at this question then. So question 7 says the curve C has the equation y is equal to that. Use the equation to complete the table below, giving the values of y to 3 decimal places. Again, it's kind of like, in principle, there's no reason why this couldn't be in degrees or radians. However, what we can always do is there's a pi in there, which rather would infer that we should be in radians. And you can always, if you're unsure about whether you're in degrees or radians for this question, you can just check it by one of the values that they've already given. So if you put it into your calculator. So in this case, we're going to program this into our calculator. And when we do, we find out that this value is 3.067. That's a 0. And this one over here is also 3.067 when we put that into the calculator as well. So that's the table completed. The region R, shown shaded in figure 3, is bound by the curve C, the x-axis and the y-axis. The line with the equation x equals 8 and the line with the equation y equals 5. Using the trapezium rule with all of the values of y from your completed table, estimate the area of R, giving your answer to 3 decimal places. Now, in this case, the trapezium rule is going to give us this area underneath the curve. So when we are putting our values from our table into the trapezium rule, it's going to give us this, an approximation to this area that I've just shaded here underneath the curve. Now, the trapezium rule, again, let's have a look. In the formula booklet, we are given the trapezium rule, which is quite nice. The first step with the trapezium rule is always to calculate what is the h for the formula. And we can see that h is b minus a over n. So h is equal to b minus a over n. Now, in this case, our b is 7, our a is 1, and the n. Now, this is the first point where students can make a mistake. Notice that in the table, we've got 1, 2, 3, 4, 5, 6 values, okay? But 6 values in the table correspond to 5 trapezia. Now, what do I mean by that? Let me just illustrate that further. So let's imagine that we have got, here's our curve, and we have got 6 values in our table. So we've got 1, 2, 3, 4, 5, 6. So let's have a look and see if I can. I think I might have drawn too many here for this illustration, but it will still serve its point. Okay, so here we've got 1, 2, 3, 4, 5, 6, 7 trapezia, okay? But we would have, in our table, we would have y0 would be there, okay? We would have yn would be there. So we'd have y0, we'd have y1, we'd have y2, we'd have y3, we'd have y4, we'd have y5, we'd have y6, and then this last one here would be y7. So we'd have, actually, in the table, 7 values in the table, okay? And there'll be 1 there, 1 there, 1 there, and 1 there. So the table for this trapezia that I've just drawn would contain 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. So you'd have, let's have a look, it would be 1, 2, 3, 4, 5, 6, 7, 8. And we've got 1, 2, 3, 4, 5, 6, 7 trapezia, yeah. So basically, there's 8 of these values, but there's only 7 trapezia. So the point that I'm illustrating is there's always going to be one more value in your table than you actually have as the number of trapezia. So going from 0 to 7, that would be 8 values in the table. But you can see that corresponds to just 1, 2, 3, 4, 5, 6, 7 trapezia. Okay, so in this case, applying that logic, what we've got here is we have got, in this particular case, we've got 1, 2, 3, 4, 5, 6 values in our table. So there will be 5 strips. Okay, so you work that out, and 7 minus 1 is 6. 6 divided by 5 is 1.2. Okay, so that's how you calculate your H. There is, in this particular case, an easier way. You can just look at the table in this case, and you can see that it's going up in 1.2s. So I would be inclined to do it both ways and use that as a check, because it's always nice for the examiner to see that you've got that working out there. Okay, but you can see it's going up in 1.1s, 1.2s for the table. So that's our H calculated. And then now it's just a question of popping all of the figures into the trapezium rule. And notice that in the way that it's written in our textbook, in our formula booklet rather, for Edexcel, we have that they've represented the trapezium rule by writing y0 and yn together at the beginning. Now that's just the first one and the last one have been grouped together. And that's because all of these ones in the middle get doubled. Okay, so we're going to have our approximation for our area underneath the graph is going to be a half times our h, which is 1.2, times by y0, which is 0, add yn, which is also 0, plus 2 times all the ones in the middle, which is going to be our 3.067, 3.067, add 3.901, add another 3.901, add another 3.067, and that's all of the values. So they're all going to get doubled. So we just put all of that into our calculator, and that gives us 16.723. Okay, so that's our approximation for our area underneath that curve. So far, so good. Now, we've got to find an estimate for R. Now, this is where there's a little bit of a tricky twist and turn in this question. So something where you could get caught out. So let's have a little think about what this turn is. Just going to draw the sketch again here. And what we've got in this case is because our curve is concave, so we've got 1, 2, 3, and we're going to have 5 trapezia, so something like that. Because our curve is concave, the answer that we've got is an underestimate. So we've got an underestimate for the area underneath the curve, okay? Because we so far in the question, this 16.723 is an approximation for this shaded area. And you can see it's just a little bit underneath what it should be because of the way that this curve lies underneath this shaded area lies underneath the graph. So we have got this is actually an underestimate of the area underneath that curve. And that is because we have a concave curve. If we have a convex curve like this, and we use the trapezium rule, what we get in that instance is we would get an overestimate because the trapezia, the top of the trapezia lies above the curve. So in that instance, we would get an overestimate. Okay, so that's generally speaking what happens. Now, what's a little bit unusual about this question is they're not asking us to find the area under the curve. They're asking us to find R. Okay, they want to know what's this area here. So what we've got to do is work out the area of the rectangle, which is just going to be 5 times 8. So the area of the rectangle is 40. And then we've got to subtract our approximation from that. Okay, we're going to take away our approximation. Now, because of this, we're actually going to be including in our value for R all these extra little bits that were missed out when we did the trapezium rule. So actually, we're going to end up with an overestimate for R. Okay, an overestimate for R, because we've got these extra bits, okay, which is so a little unusual twist just to be aware of in this question that could catch us out. Let's have a look then. So it says find our estimate for R. So we just need to have the area of our rectangle, which is 40, take away our approximation, which was 16.723, and that gives us an area of, for R, I'll write down R equals, and that's going to be 23.277. So that's our value for R. Okay, so far so good. That's part B done. 4 marks, that's a nice 4 marks to be fair. Part C, explain how the trapezium rule can be used to give a more accurate estimate. Okay, so when they want a more accurate, we could basically have more strips. More strips. Or you could say narrower strips. So basically more strips or narrower strips is going to give us a greater, more accurate answer, because if we have lots more strips, then basically the gaps between the curve and the top of the trapezia is reduced, giving us a more accurate answer. So if we increase the number of strips, our answer would become more accurate. So have more strips would make it more accurate. And then finally, state whether the answer in part B is an underestimate or an overestimate for the area of R. Justify your answer fully, and they're given 2 marks for this. And this is the discussion that I had earlier. We're going to basically say that we've got, in fact, an overestimate for R, even though the trapezium rule has given us an underestimate for the area under the curve. So they'd want you to basically say, we have an overestimate, and we basically need to just explain that it's an overestimate for R because we've had to include these extra little bits that the trapezium rule didn't get. So it's giving us a slightly bigger value for R than we would have got otherwise. And you know what, I would even draw a little sketch like that, because a picture is worth 1,000 words, and that would help to illustrate it as well. Okay, well, that's quite a nice trapezium rule question. I hope that you found that helpful, and I will see you in the next video.